Okay, we are at chapter 9, linear momentum and collisions. So let's share the PowerPoint. And if you read the intro, it talks about no, playing pool in the student center, and you notice that um, when you strike a cue ball and hit the four ball, the four ball stays stationary, and the one ball takes off with the speed of the cue ball. And we're going to learn about these collisions. But first, we're going to learn about linear momentum before we get to collisions. Um, so here's a problem. A 60-kilogram archer stands at rest on frictionless ice and fires a .03 kilogram arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after firing the arrow? Now, you can use the equations of motion that we studied in chapters, I think, 2 and 4. You can uh, try to use energy. And the truth is, none of these will answer this question. We need something more. We need more tools in our toolbox. And we're going to provide you with that with the conservation of momentum ideas. So we'll answer this question later, but we present the question now to say, well, right now there's no way of answering that. Not until we get to the conservation of momentum. All right. So here, when a system is isolated, there's internal forces only, and so we we know from Newton's third law that if there's a force, here we're showing a gravitational force of F21 and a gravitational force of F12. Now these particles are moving with velocities V1 and V2, but there is an attraction between them. Um, the uh, the mutual gravitational attraction from Newton's third law, uh, the the force of one equals the opposite the force of the other. So we know that force 1 2 equals to the negative of force 2 1. So if we add these together, F12 plus F21 equals 0. Now we're going to use that. We're going to come up with we know that mass times acceleration, mass 1 times acceleration 1 plus mass 2 times acceleration 2 equals 0. Well, what is acceleration? Acceleration is the time rate of change of velocity. So mass 1 is dv mass. I'm sorry. The first mass 1 acceleration 1 is mass 1 uh, d dt of v1 and plus mass 2 of d dt of v2. That equals 0. Now we're going to pull out um, the the d, the derivative. So d dt of mass 1 v1 plus d dt of mass 2 v2, you get the ddt of m1 v1 plus m2 v2 equals 0. Uh, and so this m1 v1 or the m2 v2, either one, we we call m times v, the mass times the velocity. We call that momentum. And here's the definition: the linear momentum p of a particle or an object that can be modeled as a particle of mass m moving with a velocity v is defined to be the product of the mass and velocity of the particle. So momentum, linear momentum, is equal to m v, the mass times the velocity. And you can separate it into its components. So momentum in x is equal to mvx, the momentum in y is equal to mvy, and the momentum in z is equal to mvz. Um, Now we know that the force equals mass times acceleration. Mass equals the time rate of change of velocity, so it's m dv dt. The I should keep up with my notes. The um, the force, the sum of the forces is equal to d uh, ddt of mv, and uh, so the ddt of mv is equal to uh, dt of linear momentum. So dpdt is the force is the time rate of change of momentum, and that is actually Newton's law. Newton's law was not force equals ma. He actually presented it was the time rate of change of momentum. So that's the way he expressed it. The time rate of change of the linear momentum of a particle is equal to the net force acting on the particle. Okay, let's do a little quiz here. Two objects have equal kinetic energies. How do the magnitudes of their momenta compare? Well, momenta one is less than momenta two. Momentum momentum one is equal to momentum two, or momentum one is equal to uh, momentum two, or there's not enough information to tell. Well, the truth is that there's not enough information because it does depend on the mass uh, uh, times the velocity. Now, kinetic energy is 1/2 mv squared. Momentum is mv. Well, you can have uh, a a small mass traveling at a high rate of speed, or you can have a large mass traveling at a slow rate of speed that have equal kinetic energies, but uh, their momenta would be different. So the answer to this one is that there's not enough information uh, for this particular problem. Not enough information is given. Now, your physical education teacher um, throws a baseball to you at a certain speed and you catch it. The teacher is next going to throw you a medicine ball whose mass is 10 times the mass of the baseball. You're given the following choices. You can have the medicine ball thrown with the same speed, the same momentum, or the same kinetic energy as the baseball. Same speed as the baseball, same momentum as the baseball, or the same kinetic energy as the baseball. Rank these choices from easiest to hardest to catch. Which one would be easiest? Well, if you work it out, if you just, it's going to be the one with the lowest speed. We know it's 10 times the mass, the one with the lowest speed. Well, if it's the same speed, then it's you're going to have 10 times the force, or at least 10 times the momentum. If it's 10 times the mass times the same velocity, it's 10 times the momentum. Um, and if it's the same momentum, well, it's 1/10 of the speed, so it'll be a slower speed. And if it's the same kinetic energy, if you work it out, the velocity of the medicine ball will be the square root of 10 of the velocity of the baseball, so it's 3.16 of the velocity of the baseball. So in order of velocity, the momentum is 0.1 v of the baseball. The kinetic energy is 3.16 the velocity of the baseball, and of course it's 10 times the velocity. I mean, it's the same velocity, but it's it's a lot of energy and a lot of momentum hitting you. So the easiest would be the same momentum, then the same kinetic energy, and then the hardest would be the same speed. And let's check it out: the same momentum, the same kinetic energy, and the same speed. Uh, Extra points if you want to calculate the you come up with the values that I came, but you can't just write them down. You need to come up with the calculations, uh, where I came up with the velocity of the medicine ball is 0.1 of the velocity of the baseball, and in C, the velocity of the medicine ball is 3.16 times the velocity of the baseball. Show me the calculations, and I'll give you extra points. Most of the time, the people that do the extra point problems, they don't need it, but that's neither here or there. I'm not going to put this assignment on paper. You have to listen to the videos to get the extra points. All right. And that, I think that ends it. That ends this section. So let's stop here.